This video is about stationary points on curves. So write the title underneath your last bit of work and read the learning objective. The learning objective is really important today, so pause the video and make sure you've had time to do that. Press play when you're ready to keep going. So today's lesson is all about stationary points. I'm going to show you 3 different types of stationary point that exist on a curve. This type, which is the same as this type. We've got this type, which is the same as this type. And we've got this and this. When I say it's the same type, it's not quite true. This is a maximum point. This is a local maximum point. What's the slight difference between a maximum point and a local maximum point? Well, a maximum point is the maximum point in the whole graph. There's no point that is higher than that point. Local maximum point, you can see everywhere above here is in fact higher. So it's only a local maximum point because it's higher, it's more, it's bigger than all the points around it. Similarly, this is a local minimum point, and this is a minimum point. This is local because there are actually points below this point that are smaller, but compared to the points around it on the graph, this is the smallest, this is the lowest, this is the local minimum. This one, however, this is just the minimum point on the graph. The last type is called a point of inflection. Both of these are points of inflection, and you can see they're neither maximum nor minimum points, nor local maximum nor local minimum points. Now, crucially, they are points. All these, the maximums, the minimums, the local maximums, the local minimums, all of these have something in common. Can you see what they all have in common? Why do you think all of these points, this one, this one, this one, this one, this one, why do you think all of them are called stationary points? Well, hopefully you realized it's because at each of these points, the gradient of the line is equal to 0. At each of these points, the tangent to the curve is flat. And so they're called stationary because the gradient at that point is neither going up or going down, it's neither positive nor negative, it is flat, it is 0, it is stationary. So if you haven't made a note of what a stationary point is, make sure you've written down a stationary point is where the gradient is equal to 0. Pause the video if you need time to do that, and press play when you're ready to keep watching. So today's lesson is about using either the first or the second derivative in order to calculate the nature of stationary points. What we mean by the nature of stationary points is it a minimum or local minimum point? Is it a maximum or local maximum point? Or is it a point of inflection? These are the 3 different types of stationary points that you are asked to find the nature of. So we're going to look at some examples now about how to do this. Make clear of the 3 different types of stationary points you can have. When you're ready to keep watching, press play. So in this video, we're going to look at examples 16, 17, and 18. And I'm also going to go through question 3i from chapter 12i, because I think it'll be helpful for you to see how I do that particular question. So, example 16, part A says, find the coordinates of the stationary point on the curve with the equation y equals x to the power of 4 minus 32x. If you think you can do this straight away, then pause the video and have a go. If you're really unclear, keep watching. So the key thing about a stationary point, what was it? How did we define a stationary point before? Well, it's a point where the gradient is equal to 0. So what we want to do is we want to find at which point the gradient of this graph is equal to 0. So I need to do that, I need to find what the gradient function is. In other words, I need to differentiate y with respect to x. So that gives me 4x to the power of 3 minus 32. Now a stationary point is where this gradient function is equal to 0. That's the key thing about finding the stationary point. You have to make the gradient function equal to 0. I'll say that again. To find a stationary point, you have to make the gradient function equal to 0. From there, you're going to solve it. Add 32 to both sides, divide by 4, cube root, you get x equals to 2. But remember, a point has how many coordinates? 2 coordinates. And at the moment, we've just found the x coordinate where the gradient is 0. So now we need to find the y coordinate on the line. So I'm going to substitute or subs in y, the original equation of the line. So I'm going to write y equals, and instead of x, I now have 2. And you can see here it's to the power of 4 minus 32, and instead of x, I've got 2. So that's 16 minus 64, which is negative 48. So where x is, what this means is where x is 2, the gradient is 0, and y is negative 48. So in other words, the stationary point on this curve is the point 2, negative 48. We've got to write brackets because it is a point on a line. It requires brackets around the coordinates. So if you missed any part of that, rewind it, rewatch it, make sure you've made notes, and then we're going to look at part B. So part B says, by considering points on either side of the stationary point, so here we have the stationary point, and we've got to consider points either side of it, to the left and to the right, determine whether it is a local maximum, a local minimum, or a point of inflection. Now let's go back to the learning objective today. I will use either the first or the second derivative in order to calculate the nature of the stationary points. So in a question like this, where we are considering points on either side of the stationary point, this situation, we are going to be using the first derivative, which means we're only going to be using dy by dx. We don't have to do a second derivative to help us answer this question. So make a purple pen note of it. When you are asked to consider points on either side of the stationary point, you are being asked to use the first derivative. So what we're being asked to do, using the gradient function, the first derivative, we know that when x is 2, this thing is equal to 0. In other words, the curve is stationary at that point. The curve, that point there, the gradient is 0. What we need to figure out is what the gradient is saying, whether it's negative or positive, either side of it. Because at the moment, it could be like that, or it could be like that. So let's say when x is equal to 1, in other words, the point before it, let's see what the gradient is at that point. Let me just draw this diagram out a bit more neatly. So 2, negative 48. We know the stationary point is there. We know that when x is 0, y is 0. Just looking at this, I can see that. So we know it goes to this point. But at the moment, we need to actually figure out, using the points either side of it, whether it's a local maximum or local minimum. Because it could be doing this, or it could be doing this. Or it could be doing some variation of that as well. So let's look at when x is 1. 4 bracket 1 cubed minus 32. That's the same as 4 minus 32, which is obviously negative 28. So when x is 1, the gradient is negative 28. So the gradient is going down negatively at that point. Why did I choose when x is 1? It was because that is a point that is to the left of x equals 2. Remember, I'm considering points on either side of the stationary point. So what do you think the other value of x I'm going to consider is going to be? Hopefully it's clear to you. We're going to do when x equals 3, because that is 1 up from x equals 2. It's the point to the other side of it. So dy by dx equals 4 bracket 3 cubed minus 32, which is 4 times 27, which is 108 minus 32, which is equal to 76. 76 is obviously bigger than 0, which means we have a positive gradient where x is 3. So let's just understand this. When x is negative 1, we've got a negative gradient. When x is 2, we've already figured out, we've got a stationary point. The gradient is 0. And when x is 3, we've got a positive gradient. So therefore, must our stationary point be a local minimum point, a local maximum point, or a point of inflection? Well, you can see from the shape of these gradients, it's going down, then it's going flat, then it's going up. It must be a smiley face. So using the points either side, using x equals 1 and y equals 1, I've figured out, sorry, x equals 1 and x equals 3, I've managed to show that this is a local minimum point. So example 17 says, A, find the coordinates of the stationary points on the curve with that equation. So to find a stationary point, that is where the gradient is equal to 0. So I need to find the gradient function by differentiating y with respect to x, which means I get 6x squared minus 30x plus 24. Now the key point about the stationary point is that the gradient is 0. So what I'm saying is that this must be equal to 0. If you think you can answer the rest of this question from here, then have a go. If you want to have a go at part B, then feel free to do so and press play when you're ready to keep watching. So what I need to do now is I need to solve this quadratic equation. With an equation, I can divide by the highest common factor, as long as I do it to both sides. Dividing everything by 6, I get x squared minus 5x plus 4 equal to 0. I'm now going to factorize this. So I get minus 4 and minus 1. So therefore, x equals 1 and x equals 4. So that means there's going to be 2 stationary points on the curve with this equation. At the moment, I've found what x is to find what y is, because I have to find both coordinates, I'm going to substitute into y. So I'm going to substitute into the original equation. So I'm going to do that underneath to keep it neat. When x equals 1, y equals 2 bracket 1 cubed minus 15 bracket 1 squared plus 24 brackets 1 plus 6. Just so you can see where we're going with this, when x equals 4, because remember there's two solutions, y equals 2 bracket 4 cubed minus 15 bracket 4 squared plus 24 bracket 4 plus 6. If I type all that into my calculator, I get 4 over here, and if I type all this into my calculator, I get negative 10 there. So the stationary points are 1, 4, when x is 1, y is 4, and 4, negative 10, when x is 4, y is negative 10. So that's part A. Part B says, find d2y by dx squared and use it to determine the nature of the stationary points. So going back to the learning objective again, as I said right at the beginning, to find the nature of stationary points, you can either use the first or the second derivative. This question is telling us we need to use the second derivative because it's telling us we have to find d2y by dx squared. So the first thing I'm going to do is I'm going to find d2y by dx squared. So part B, keeping in mind my original differential, the first derivative was 6x squared minus 30x plus 24. d2y by dx squared is equal to 12x minus 30. So what this means is the gradient of the gradient is 12x minus 30. Now don't worry too much about this for the time being, but what I'm going to do is I'm going to find the second derivative when x is 1. So using my previous answer over here, when x equals 1, d2y by dx squared equals 12 bracket 1 minus 30, which is 12 minus 30, which is negative 18. What this means is the gradient is always decreasing. Because it's a negative number, it means the gradient is decreasing. So imagine a curve like this. In this situation, the gradient at this point starts off like that. That's a tangent. It's really steep positive. At this point, it's getting a bit more negative. Sorry, it's getting a bit less positive. It's still positive, it's less steep. At this point, it's still positive, but it's even less steep and it's approaching being flat. Now at this point, the stationary point is obviously flat. All the way through this curve, the tangents are decreasing in their gradient. They're constantly getting lower and lower and lower in their gradient. The steepness of the line is getting less and less and less until actually we reach a point over here where they're starting to be negative. And they get more and more steeply negative as you go further along the curve. That is what the second derivative being negative means. And because of that, if the second derivative is negative, it means we're dealing with a local maximum point. So therefore I can say, therefore this is a maximum point, or local maximum point. I want you to pause the video and have a go at finding whether or not this point here, this one, is a local minimum or a local maximum point in just the same way. So pause the video and have a go at doing that now. So again, we're using this differential equation, which means we're using the same second order derivative. But this time the difference is we're dealing with when x is 4. We're saying when x is 4, d2y by dx squared is 12 brackets 4 minus 30, which is 48 minus 30, which is 18. What this means is that at all times the gradient is increasing. So I want you to imagine this curve here starts off very negative. Then it gets a bit less negative. Then it gets almost flat. And then it gets actually flat. And then it gets a bit positive. And then it gets really positive. And then it becomes a really positive steep line. At all times over the course of this curve from left to right, the gradient is increasing. Because this number here is positive, it means that the gradient is constantly increasing. We don't need to worry about the actual values, negative 18 and positive 18. What matters is whether or not they're positive or negative. Because it's positive, we know we're dealing with a curve like this, and so therefore this point here must be a local minimum point. And this bit here, the red, that is answering part B. So that was example number 17 from the textbook. If you want to rewind any part of that to make it clear to yourself, then please do so. And I'm going to get started with example 18 when you're ready. I'm just going to leave a bit more space myself. So, example 18, part A says the curve with equation y equals 1 over x plus 27x cubed has stationary points at x equal to plus or minus a, and we have to find the value of a. If you think you can do this on your own, in fact everyone at this point, pause the video and have a go at doing this and press play when you're ready for me to go through it. So, this is basically asking us to find the stationary points, or find the x values of the stationary points. So for part A, I know that y equals 1 over x plus 27x cubed. So I'm going to rewrite it nicely so that it's easier for me to differentiate. Remember, 1 over x is the same as x to the power of negative 1. I'm now able to differentiate this. I'm going to do dy by dx equals negative x to the power of negative 2 plus 81x to the power of 2. Now a stationary point, that is when the gradient is equal to 0. So what I'm saying is 1 over x squared, that remember is the same as this. These two things are equal. Plus 81 over x, 81x squared, we're saying that is equal to 0 because it's a stationary point where the gradient is 0. I'm now going to solve this, so I'm going to add 1 over x squared to both sides. And I'm going to multiply both sides by x squared. Divide both sides by 81. And then the fourth root of 1 over 81 is plus or minus 1 over 3, because 3 to the power of 4 is 81. So that means, going back to the question, x is plus or minus 1/3, and over here it said x was plus or minus a. Because they've already written the plus or minus for us, what we can say is that a is equal to 1/3 specifically, not positive or negative, because that's written there already. Part B, I want you again this time to pause the video and have a go at answering part B. Press play when you're ready for me to go through it. Alright, so part B says sketch the graph that you're dealing with in question 1, part A. So to sketch the graph, we always go through the same process. Step 1, what's the shape? Well, to be honest, this is like combining a reciprocal with a cubic. I don't really know what the shape is. So if I don't have any graphing software, I'm a bit stuck. So I can't really deal with that for the time being. Step 2. What was step 2? Do you remember? Roots when? Y equals 0. Alright, let's try that then. So we've got 0 equal to 1 over x plus 27x cubed. And then I'm going to have, so I don't know what this purple pen thing's annoying. Don't know what that's about. Then I'm going to take away 1 over x from both sides, because it's not really easy to factorize that. I'll times both sides by x, and I get negative 1 equals 27x to the power of 4. Then I'm going to divide both sides by 27. And at this point, I'm thinking to myself, the fourth root of negative 1 over 27, that's impossible, because no number to the power of 4 would give a negative. So this graph doesn't have roots. So step 2 I can't do. Step 3 I would usually sketch, but I'm in no place to sketch right now, so I can't do that. Step 4, y-intercept when x is 0. Well, looking at my equation, y equals 1 over x plus 27x cubed, x can't be equal to 0 because it's on the denominator of a fraction, and that would cause the fraction to be undefined. So there's no y-intercept. The graph doesn't cross the y-intercept. Looks like the y-axis, sorry, the graph doesn't cross the y-axis. The y-axis looks like it's going to be an asymptote. So we're a bit stuck at this point. The usual route that we go through for sketching a graph is not available to us. We can't do any of those things. The only thing we've managed to find is that it doesn't cross the y-axis. But we do know that this curve has stationary points. We know the stationary points are when, let's go over here, when x is positive 1/3 and when x is negative 1/3. So what we can do is, if we find the full point, in other words, find the y coordinate that goes with those x coordinates, and also if we figure out the nature of the stationary points, so we figure out whether they're local minimum points or they're local maximum points or they're points of inflection, if we can figure out that, then we'll probably have enough information to be able to sketch the graph, even though we weren't able to do all these steps over here that we normally do. So this is our plan. First, find the y coordinates for the stationary points. Then find the nature of the stationary points. From there, we also can use this step 4 that we did earlier here, which showed us that there was no y-intercept. Maybe, hopefully, at that point, we'll be able to sketch this graph. So let's have a go. So to find the y coordinates for the stationary points, we know that the graph is y equals 1 over x plus 27x cubed. So going back to our solutions, when x equals 1/3, y equals 1 over 1/3 plus 27 1/3 cubed. We can also say when x equals negative a third, because remember over here there were two solutions, y equals 1 over negative a third plus 27 negative a third cubed. You can calculate all this out, and obviously you can type it into your calculator. You end up with y equal to 4 here, y equal to negative 4 here. So the stationary points are 1/3, 4, negative 1/3, negative 4. Why do you think I've extended this line for my answer beyond the actual coordinates? Well, it's because I want to say the nature of these turning points. These stationary points. I know they're stationary points. I want to say, are they max or min or points of inflection? So now I have to find the nature of the stationary points. So to do that, it's usually more efficient to find the second derivative. Let's zoom out, find the first derivative, which is over here. So dy by dx, we already figured out, was negative x to the negative 2 plus 81 x squared. And so to find d2y by dx squared, it's going to be 2x to the negative 3 plus 162x. When x equals a third, because remember I'm finding this stationary point first, d2y by dx squared equals 2 a third to the negative 3 plus 162 times a third. You end up with positive 108. Now it doesn't matter what that number is, this 108. What matters is that it is a positive 108. Now if it's a positive 108, that means the gradient is constantly increasing. So if this number is bigger than 0, it means the gradient is constantly increasing, so the curve is going to look like that. And if the curve looks like that, then the stationary point, must be a local minimum point. So what I want you to do now, after you've made your notes, is I want you to try and do the same thing when x is negative 1/3. I want you to figure out the nature of the stationary point when x is negative 1/3. So pause the video and have a go. Press play when you're ready to keep going. So again, we're using the second derivative. We know that d2y by dx squared is equal to 2x to the negative 3 plus 162x. And so we're going to substitute this time x for negative 1/3. So let's write it nicely. When x is negative 1/3, d2y by dx squared equals 2 brackets negative 1/3 to the negative 3 plus 162 to the negative 1/3. Touch the times by negative 1/3. If you do all that into a calculator nicely, you get negative 108. Negative 108, it doesn't matter the numerical value apart from the fact that it is less than 0. Because it's less than 0, I know that the gradient of the curve is forever decreasing, which means it looks like that, which means the stationary point is at the top. So this is a local maximum point. Now that we know our two maximum minimum points, our two stationary points, and we know that what they look like, we can combine this with what we did in step 4 over here, which is the fact that it doesn't cross the y-axis, to sketch our curve. So we've got negative 3, 4. Cool, let's call this one point A, 1/3, 4. So that is a third of the way along from the origin and 4 up. So call that A. And then we've got B, negative a third, negative 4. Now we know A is a local minimum point. We also know it's tending towards the y-axis. So A looks like that. If the y-axis kept going, it would get closer and closer, but it wouldn't reach it. And B, a local maximum point, again, it's going to tend towards the y-axis, but it's never going to reach it. So B looks like that. And so our sketch is what you can see in blue. This is a very long question. It's quite a difficult question. I would be surprised if you did not need to rewatch any part of this. So if I were you, I would go back through it, rewatch it. Maybe before you rewatch it, you try and answer it yourself, and then watch the video and watch how I do it. So make sure your notes are clear, and then we'll do one more example because I think it'll be useful for you to see how I do it. So press play when you're ready to keep watching. So the last thing I want to go through is I want to do an example with question 3, and I'm going to go through this one here. So we can ignore all the other parts. You'll have to look at show my homework as to which bits I want you to do. Question 3 says, find the coordinates of the points where the gradient is 0 on the curves of the given equations. So that basically means find the coordinates of the stationary points. Establish whether these points are local maximum points, local minimum points, or points of inflection in each case. So I want you now to have a go at doing this on your own. Pause the video, have a go. Press play when you're ready to keep watching. So, to find the points where the gradient is 0, if I know that y is x to the power of 4 minus 12x squared, I know dy by dx is equal to 4x cubed minus 24x. I know that where the gradient is 0, these points will be stationary. And now I'm going to divide everything by 4 to make it a bit easier. Factorize, solve. I get x equal to 0, and I also get x squared equal to negative 6. Sorry, x squared equal to 6, which means x equals plus or minus root 6. So I'm going to write those out slightly apart because it's going to help for my working for the next part of the question. So these are the 3 solutions to that equation, which means these are the 3 x values where the gradient of this curve is equal to 0. But if I want to find the coordinates of the points, what do I have to do next? Hopefully you remember, we have to sub into y. So when x is 0, y equals 0 to the power of 4 minus 12, 0 squared, so obviously it's 0. So the first stationary point is 0, 0. When x is 0, y is 0. When x is negative root 6, y equals negative root 6 to the power of 4 minus 12 negative root 6 squared. Negative root 6 times negative root 6 is positive 6, and then do the same again because it's to the power of 4. We have 36. Negative root 6 times negative root 6 here is positive 6. Positive 6 times negative 12 is negative 72. That's negative 36, which means the coordinates are negative root 6, negative 36. And over here, when x is positive root 6, y equals positive root 6 power of 4 minus 12 positive root 6 squared, which is the same as 36 minus 72 again. And so again, we get negative 36. So the final turning point is that. We've got three keep calling them turning points. They're not turning points. They could be points of inflection. So these are stationary points. We now have to figure out the nature of each of these stationary points. So to do this, I'm going to use the second derivative. It's more efficient than finding the first derivative points either side like we did in the very first example. So using this, the first derivative, I'm going to differentiate again, which gives 12x squared minus 24. So now what I need to do for each of these 3 points, when x is 0, x is negative root 6, and x is positive root 6, is I'm going to find what d2y by dx squared is. So we've got 12 bracket 0 squared minus 24, so that's negative 24. As I keep saying, it doesn't matter what the number is, what matters is it's less than 0. And if it's less than 0, the curve is going to be constantly decreasing, making this a local maximum point. Pause the video and have a go at doing the other 2 points on your own if you weren't sure about the first one, but you now think you've got it. Press play when you're ready for me to go through it. So when x equals negative root 6, d2y by dx squared equals 12 brackets negative root 6 squared minus 24. Remember, I'm substituting this into here. So that is 12 times 6, which is 72 minus 24, which gives me 48. Doesn't matter the numerical value. All that matters is that 48 is greater than 0, which means I have a curve that is constantly increasing, making this point a local minimum point. Final one. Again, if you weren't sure about the other 2, but you think you now got it, pause the video and have a go yourself. X equals root 6, d2y over dx squared equals 12 bracket root 6 squared minus 24. So that is 72 minus 24, which again is positive 48. 48 is greater than 0, so we know this is what it looks like, which means we know this is a local maximum point. There's quite a lot of steps to each of these questions, guys, but actually the process is fairly repetitive. So make sure your notes are clear. Have a go at the questions as it says to on Show My Homework, and obviously email me or Miss Kuba if you're having trouble with anything.